Yes.
The first question I had was number 10. It's an electron moving at 4 times 10 to the third meters per second in a 1.25 Tesla magnetic field. Experiences magnetic forces at 1.4 times 10 to the negative 16. What angle does the velocity of the electron make with the magnetic field? I didn't really have a question about the answers, but other than like why are there two of them?
You ultimately end up with a there's a cross product in there, and the magnitude of the cross product, if I had A cross B, the magnitude is A B sine of theta. So if I know that the sine of theta is equal to 0.5, well, if I bring up my unit circle, 0.5 would be that angle right there, or that angle right there.
Okay.
So,
It's gonna be
30 degrees and 150 degrees,
Yeah.
both would give you the same angle, or same sine value. Now, also in this particular problem, it says it experiences a magnetic force of 1.5 times 10 to the negative 16 newtons. That doesn't really, that's the magnitude, not the. There's no direction involved, so that's just the magnitude. So actually, if that's just the magnitude, there are 4 angles.
and then
And by the way, if you did an arc sine is just going to give you the first quadrant angle.
You know, after that, could you just like subtract that from 180 and get your second level?
Yeah.
then number 55. I just couldn't find the picture, so it was a little confusing. I don't know if you had the picture.
55, figure 22.57.
Yeah.
Sorry, long straight wire near rectangular current loop, direction of magnetic, the total force on the loop. So the picture is and the current's going that way, 15 amps. And then there's a current flowing through here of 30 amps. So you find the force between these two wires and the force between these two wires. And so this would have two forces acting on it. Like add. You might be adding a negative. Well, actually, one in the opposite direction. Is that what you needed? Or do you need me to keep going?
Just the distances, like the 0.075 meters. Where are those?
That's the 7.5 centimeters. This is 10 centimeters. 0.1 meters. And the other one is 30 centimeters. That's supposed to be a rectangle.
Yeah. So to get the 0.175 meters for one of the equations, you just add that.
Yeah, it's so that's the distance of 0.075, and that's the distance of 1.75.
Does the 0.3 meters matter?
Oh, it does in the fact that the formula, I forget how this book presents it. It might give you force per length, but it was use of naught I1 I2 over 2
It does give you force.
R 2 pi R L, something like that. And that L right there is the 0.3 meters.
Also, in this question, F3 and F4 are the same, but why are F1 and F2 not the same? Like, what's the discrepancy between?
Why are these the same?
Well, so F1 is this force,
From the top one or the bottom?
The top one.
Top one, opposite directions, yeah.
And then F2 is up, and then it's left on the right, so the force is that way. And then it's the opposite. So the two outside forces are the same, but the two middle ones aren't the same.
These two right here are, every part of it is for each part on this, which is a certain distance away, there's one over here which is the same. In this case right here, this is farther away, so the force on this bottom part should be less than the force on the top part in magnitude.
Okay.
But these, since they're both equidistant from this line, there'd be some canceling.
Well, in this, they're like drawing at different points on this side. Does that matter? Or is that just,
Different points on the side?
yeah?
It shouldn't, but let me,
That's just like a drawing, like a graph thing?
that's chapter 23. That's not gonna help a lot. Come on. I have to. That's the textbook. Yeah, let me see what, you have it printed out?
Yeah. See like how this one is lower than that one.
Oh, I think that's just for style points.
So like,
So it's not,
you just assume that they're at the same point.
yeah,
Okay.
yeah.
Another question that I had was the one right after 56. I didn't really have a question about the first one, but like when you start doing the angles with all of the functions, I got a little lost.
All right, this was,
56, I think. It was 56. You had
you said 56, you got the three currents.
Yeah.
You got messed up by the angles?
Yeah, like the second part, the first part is just the equations, like that equation we just put up there, and the second part was, like
Adding.
FAB sine 30 minus FAC sine 30.
Yeah, on that particular one, let's see, it's coming out and those two are in, so I got one coming out and I have two going in. I know if they're going in opposite directions, if current's going in opposite direction, it's gonna push out, as demonstrated in the lab last week. So this is gonna have a force, let's see, do they label it A, B, and C?
Yeah, they do.
Which one is,
A is the top one, B is the left, and C is the right.
okay, so A, B, and C. So the force on A from B is going in that direction. The force on B from A is going in that direction. These are also in opposite directions, so they're gonna be pushing away from each other. The force on A from C and the force on C from A. And then these two will attract each other. So the force on B from C and the force on C from B. So when you add vectors, direction matters. And so it depends on how you want to do it, but I believe it's an equilateral triangle.
Look
10, 10, 10, yeah. So this angle right here would have to be 60 degrees. That's 60 degrees. Likewise, that's 60 degrees. And that's 60 degrees. So you just need to break it up into horizontal and vertical components. That's where that's coming in.
Oh, is that what, all of that is, that's all it is, it's just breaking it up?
That's probably the hardest part. The magnitude of the force is just a plug and jug.
Can you show doing that? 'Cause you said
Break
you
it
have
up
to-
or?
Yeah, the breaking up into the I hat and J hat, I would assume.
Alright. So if I define my I hat, J hat in the typical way. Then, I have a vector here, FAB, 60 degrees. That's polar form, assuming we've already calculated that number. That's gonna be FAB, the magnitude of FAB, times the cosine of 60 degrees I hat, plus that magnitude, times the sine of 60 degrees J hat.
Where are we getting 60 degrees from again?
Equilateral triangle. That's 60, 60, and 60. That force is along this line right here. Since that's a 60-degree angle there, that's a 60-degree angle there.
Yeah, okay. Oh, okay, I got it.
And for the thing right above that, the F cosine 60 degrees, is that the same formula for all three of them?
You gotta watch out for plus and minus signs. But yeah, you could do it for the 4 vectors we would need to break up.
And the
Those
ones you
all
would add would be going in the same direction or the opposite direction?
The ones that you add, well, I got the 2 forces right here.
Mm-hmm.
So one of them is gonna be, so that's this right here. FAC is equal to, that's FCA, no, AC. I said it right the first time. Somebody changed the setting on this. I suspect the board did. FAC. Well, it's going up in the second quadrant. And so I could break it, use the base angle, and just do FAC cosine of 60 degrees I hat, but it's going to the left, so that's negative,
Okay.
plus FAC sine of 60 degrees J hat, but it's going up, well, that's still positive, so I keep that.
Okay, that makes sense.
Alternatively, if I treat all at 0 degrees, 90, 180, and so on, that angle right there is 120 degrees. So I could just do FAC cosine of 120 degrees I hat plus FAC sine of 120 degrees J hat, and the minus sign would come out of that. I don't need to. If I think through the angle based upon that's 0 degrees and positive going this way, then I don't have to think about plus and minus here. It's gonna come out on the calculator here.
So that you just added all those angles together basically and did that one for those 2 vectors.
Once I calculate that out, I would just add them. These 2 are gonna cancel out because, well, they're active inverses. And so it'll just be twice that.
So once you add them, and then, so if you add those 2, would that be the final answer for the force on A?
Yes.
Okay, so, oh, and this, on the example is using, you find the magnitude and then the angle, but we can just do it in that rectangular form?
Well, yeah, I assume that we know what that is, but
Well, I'm just saying, on here he's giving the answer in like, he was giving the magnitude and then like 10.9 degrees. I'm just saying that we can do it that way and we don't have to do it this way.
oh, they put the final answer in polar form?
Yeah.
If it doesn't specify, then I don't care. Some people will do it just because they enjoy the math. Sometimes you need any excuse to work a little trick into your life. You know what I'm saying? You with me?
One more question I had was question 80. Not really about like the equation or anything, but eventually you're just changing the formula and you get 2 pi over v times mv qb. How did we plug in that mv qb?
All right, so show the period of a circular orbit of a charged particle is that. So how'd you get MV QB?
Yeah, for A, the first question. Cause it starts with the T equals 2 pi R over V.
Alright, so I know that if I've got a, magnetic field that's coming out, and I have a charge moving in, some Q at some speed V heading into it, it's gonna assume Q is positive. Right hand rule, my charge is going that way, magnetic field is going into the bore, the force on it is up. Let's make sure I did that right, so also it's going this way, it should be down. Oh, I did make the same mistake the other day. Particle's going that way, magnetic field's going out, the force is acting down. So it's gonna curve around like that. The force acting on it is going to be perpendicular to the motion every time, because the force Q V cross B. And so it's got, force has to be perpendicular to both the velocity and the magnetic field. Because the force is perpendicular to the motion, we have centripetal motion. So that's got to be equal to mv squared over r. So that's Q V B equals mv squared over r. One of the v's cancels out. And so if we solve for r is mv over qb. And the period, the circumference, let's see how to go, I know that speed is distance over time. And if I'm talking about one cycle, that's a circumference divided by the period, so 2 pi r over t. So t is going to be 2 pi r over v, just solve for t, and then plug that in. And that v is going to cancel out with that v. Did I go too fast?
No, I got it. You just did the QV cross B and then changed it into that.
Yes.
So I understand all those equations, but in the problem it says T equals 2 pi m over qb.
Yeah. All right. So if I plug this into here, my period would be 2 pi over v times r, which is mv over qb. That, the speeds cancel out. And I'm left with 2 pi m over qb.
So it's just, they equal each other, those equations? Or,
The first part of the problem was to show that show that the period is equal to that. Was there a question? Did I miss your question?
no, I got it.
Okay. No other questions?
So number 42, it involves torque.
Yes.
Is it always going to be the, I think that's NIAB sine of phi? Is that just a general torque equation relating to?
NIAB.
Yeah.
This is that a little a, little b?
No, they're big A and big B.
So N is the number of coils. Torque is going to be U cross B. U is IA. So NIAB, is that what you said? NIAB?
Yeah.
Yeah. For a perpendicular. There's a cross product in there.
Well, there is sine of phi at the end of it too.
Oh. So it's a mu cross B. This is a mu that I don't think I introduced in this class. This is a different mu than all the other ones we've dealt with. This is the magnetic dipole moment, which is equal to the current going through the loop times the area of the loop. So area of the loop, if that's my wire right there, A is that area right there.
So where does the N come from?
Number
Is
of
that
coils,
just
each
for-
one-
and it's just, you just add an N if it's a, I don't know, the solenoid?
Yeah, or several coils. I mean, if good enough for 152. I mean, the more coils I add, I guess if it's still a uniform field. But, yes. $150 turn loop of wire. Okay.
And I have another question on 18, you have E equals VB in the answer, and then, but in 23, you have E equals VLV.
All right, TV CRT moves with the speed, in direction perpendicular to the Earth's field. All right, what's your question again?
So in 18, you have E equals VB written in the answer, but in 23, you have E equals VLV.
You said 23?
Yeah.
You said 23.
23.
The hall voltage?
Yeah.
BLV is the motional EMF.
Yeah.
And